Hi, welcome back to General Chemistry 1. I'm Dr. Fang Xu. Today, let's talk about the last topic in Chapter 10, VSEPR theory. This topic based 100% on a correct Lewis structure. So make sure you can write the Lewis structure. You master the knowledge about Lewis structure. Okay, so what is VSEPR theory? It's actually called valence shell electron pair repulsion theory. So it goes like, to minimize the repulsions, each group of valence electrons around a central atom is located as far as possible from others. So basically it means if you have a central atom, it has different groups attached to it. And because atoms are bonded together with electrons, so each group can be counted as an electron group. Okay, these electron group does not like each other. They repulse each other and want to occupy in the 3D space as far away from each other as possible. So when we talk about a group of valence electrons, possible groups are lone pairs, a lone electron, or any type of a bond. Single bond, double bond, triple bond is considered as a bond. Okay. And only groups on the central atoms affect the shape. Electrons on atoms other than the central atoms do not. And finally, VSEPR is used to determine a molecule's shape in 3D space. Okay, and those are based on, how many groups of electrons around central atoms, and the group of electrons need to be determined based on Lewis structure. So for the VSEPR theory, in order for us to more easily determine the shape, we have a VSEPR designation. It's called A, X sub m, and E sub n. So this A means the central atom, and there's only one central atom. Okay, and X means the surrounding atom. It can refer to any type of the bond. A single bond connects to an atom. A double bond also connects to an atom. A triple bond also connects to an atom. So we can simplify this question and just count how many surrounding atoms are there. So that subscript M is the number of surrounding atoms. The uppercase E refers to the non-bonding valence electron group attached to A in a Lewis structure. The subscript N refers to the number of non-bonding electron groups. Okay, as I said, non-bonding electron groups can be either a pair of electrons or a lone electrons. Okay, so a few things to keep in mind. Both X and E, both atom and lone pair or electron pairs or lone electrons are the groups attached to A. Okay, we only care about what is around A. And second, X, the atom, is visible. E, the electrons, are not visible. So when you think about how the molecules occupy the 3D space, we need to count both X and E, both atom and electrons, to think how they occupy the 3D space. But when we talk about the shape of the molecule, the electrons is not visible. So we kind of don't include electrons when we talk about the shape of molecule. In the simplest case, the central atom bonds to the same surrounding atoms. All the bonding environment are the same, so we can have a list of ideal molecule shapes. Let's take a look at a few simplest situations, the ideal molecular shapes. That refers to the central atoms that does not have any lone electrons or electron pairs. It binds to all the surrounding atoms, and those surrounding atoms are the same. Okay, so I took this picture from the textbook, and it refers to all the ideal molecule shapes, and to remember them and to remember the bond angles between them. And that refers to the AXM. We don't have electrons, and all the X are the same atoms. When M equals to 2, these two atoms wants to get far away from each other as possible, so they occupy these opposite directions, and the shape is a linear shape. The bond angle is 180 degrees. If we have 3 atoms around central atom, if M equals to 3, we have the ideal molecule shape as trigonal planar shape, and the bond angle is 120 degrees. all of the ideal molecule shapes here are of high symmetry. So if not specifically mentioned, all the bond angles are the same. When m equals to 4, we have the tetrahedral shape. The bond angle is 109.5 degrees. When m equals to 5, now we have the trigonal bipyramidal shape. In this case, we have two bond angles. The top or the vertical line, we have two atoms, and those two atoms have 90-degree angle with any of the three atoms in the middle planar. Well, all of the three atoms in the middle plane have 120 degrees to each other. When m equals to 6, we have the octahedral group. And in the octahedral group, any bond angle is 90 degrees. A few things to keep in mind. First, remember the ideal shape and bond angle. Like, remember them clearly. Those can be on the exams and tests. And only AXN molecules with all X the same have an ideal shape. If we have other cases, for example, if we include some lone pairs or electron pairs, then the shape will be distorted, the bond angle will be distorted. Okay, and we will talk about that in a case-by-case study in the next few slides. Okay, so if we bind the XR different atoms, the shape will still be the same, but will be distorted. Okay, so let's take a look at the case when m plus n equals to 2. Okay, so when m plus n equals to 2, the shape will be a linear shape. The bond angle will be 180 degrees. In this case, we don't have any electron pairs on the central atom. So even though X may not be the same, it's still the linear shape. A few examples: beryllium chloride, it has 180 degrees. You see, I have the chlorine, beryllium, chlorine, and this is a linear shape, the same as carbon dioxide. So as you can see here, if we have a single bond or we have a double bond, it does not matter. What it matters is how many atoms are bonded to the central atom and how many electron pairs are there in the central atom. So in both of the case here, it's a linear shape with 180 degrees. All right, so let's move on to the m plus n equals to 3 case. And in this case, since we have multiple X and we may have electron pair, we'll just talk about a easier situation, assuming all X are the same atoms. So if we don't have any electron pair in the central atom, we have the trigonal planar shape. The bond angle is 120 degrees, like the case of boron trifluoride, or like the case in the nitrate. Okay, so however, if we have a lone pair can include 2 electrons. If we have a lone pair in the central atom, then because the electron is invisible, so when we talk about the shape of the molecule, we will cover up this electron and see the shape left over of this, this molecule. So in this case, it will be a band structure or V-shaped structure when m equals 2, n equals to 1. The bond angle will be smaller than 120 degrees, like the case in the selenium 2 chloride. Okay, so in this case, I would like to mention one more thing, that when we talk about these electron pairs, we only care the electron pairs in the central atom. When we have electron pairs, say here in the chlorine atom, it does not matter at all. It does not connect to the central atom. It does not matter at all. So we don't count those electrons on the surrounding atoms. We only count the electron pairs in the central atoms. And one pair will count as n equals to 1. If we have 2 pairs, then n equals to 2. Okay, so let's take a look at m plus n equals to 4. Again, assuming all X are the same atom, if we don't have any electron pairs, then the shape of the molecule is tetrahedral shape. The bond angle is 109.5 degrees. An example is methane. However, if we have one electron pair on the central atom, the leftover shape of this m plus n equals to 4 is a trigonal pyramidal, that m equals to 3, n equals to 1. The bond angle here for the tripyramidal is smaller than 109.5 degrees. An example is ammonia. Okay, so then in this case, the central atom may have 2 pairs of electrons. In this case, the leftover molecular structure is a band structure that m equals to 2 and n equals to 2. The bond angle here is also smaller than 109.5 degrees. An example here is a water molecule. So just pay attention. Here we see a second time to see a band structure. In the m plus n equals to 3, in the previous slide, we also had a band structure, but that band structure has a bond angle smaller than 120 degrees. Well, here, when m plus n equals to 4, the bond angle is even smaller. It's smaller than 109.5 degrees. So as you can see here, all the benchmark of the bond angle is used as the bond angle in the ideal shape. When m plus n equals to 5, then we have the ideal shape of trigonal bipyramidal shape. Okay, again, assume all x are the same atom. When m equals to 5, the shape is trigonal bipyramidal shape. And in this shape, it's the most special case that it has 2 different types of bond angles. The bond angle between an axial position atom and equatorial position atom is 90 degrees. And the bond angle between all of the 3 equatorial positions are 120 degrees. An example of the molecule is phosphorus pentachloride. Also, in this case, we may have electron pairs on the central atom. If we have only 1 electron pairs in the central atom, the leftover shape is a seesaw shape. M equals to 4, n equals to 1. The bond angle is smaller than 90 degrees when we talk about the axial position to the equatorial position. The bond angle is smaller than 90 degrees. And the bond angle between the 2 equatorial position atoms are smaller than 120 degrees. An example here is the sulfur tetrafluoride. Then, if the central atom has 2 pairs of electrons, in total 4 electrons, the leftover structure is a T shape that corresponding to m equals to 3, n equals to 2. The bond angle here in the T shape are smaller than 90 degrees. An example is bromine trifluoride. Finally, if we have 3 pairs of electrons in the central atom, the leftover structure of the molecule is a linear shape. M equals to 2, n equals to 3. The bond angle equals to 180 degrees. So every time you determine the linear structure, the bond angle has to be 180 degrees. The example of this type of molecule is item 3 minus Ni. Okay. Finally, let's talk about case m plus n equals to 6. Again, assuming all x are the same atoms, the ideal shape is octahedral shape. M equals to 2. The bond angle, any of the bond angle here is 90 degrees. The example is sulfur hexafluoride. Also in this case, the central atom may have some pairs of electrons. If the central atom has 1 pair of electrons, the leftover species is square pyramidal. M equals to 5, n equals to 1. The bond angle here will be smaller than 90 degrees. Okay, an example is iodine pentafluoride. And finally, if the central atom has 2 pairs of electrons, the leftover shape of the molecule is a square planar shape. M equals to 3, n equals to 3. The bond angle here, because it's a square planar, the bond angle is 90 degrees. An example here is xenon tetrafluoride. All right. Now we describe every possible situation of m plus n, m and n. So now it's about time to try it out. Let's take a look at VSEPR problem. So when we solve the VSEPR problems, usually it gives you a molecule structure and asks you what is the shape of the molecule, what is the bond angle. Okay, so for that, we can solve the problem in a few steps. Step 1 is to draw the correct Lewis structure. Lewis structure here is so important because we need to know how many lone pairs are there to determine the value of n. If the Lewis structure is not drawn correctly, it's very unlikely to get a correct answer of the VSEPR problem. So please pay attention to the Lewis structure. Once we have a good Lewis structure, then we can determine the m and n value in the VSEPR designation Ax sub n, E sub n. And then once we have this formula Axm, E sub n, we can assign the shape and bond angle. So there are a few ways to do a VSEPR problem. One is to remember all different combinations of Axm, En, and then once you see the designation, you come up with the shape, which requires a lot of memorization. The way I prefer to do is to remember the ideal structure. Then from that point, see how many lone pairs you have and what are, when those two lone pairs are invisible, to see what's left over of the ideal structure. So let's take a look at example. Determine the shape and bond and the range of bond angles of COCl2. You may take out the scratch sheet and try to work out the problem yourself first. All right. So in this case, we have one carbon here. So first we need to determine the structure of this molecule. So we have one carbon, one oxygen, and two chlorine. So either carbon and oxygen have less number than the chlorine. But if we have choice between carbon and oxygen, we will choose carbon to put that in the center. Okay. So, and also because the carbon is less electronegative, so we put that in the center than instead of oxygen. So then we can draw a Lewis structure. I'll skip that for now. The correct Lewis structure drawn is like this. Carbon in the center, it has a double bond to oxygen and two single bonds to two chlorine. Okay, so that corresponding to 3 atoms around the central atom and does not have any electron pairs in the central atom. So the designation is AX3. So once we know the AX3, we corresponding to the ideal shape of 3 atoms, that's trigonal planar shape. But in this case, since oxygen and chlorine are not the same atom, so the shape we have will be a distorted trigonal planar shape. And because it's a distorted trigonal planar shape and we have different types of atoms, we can say now the bond angle does not equal to 120 degrees. Whether it's smaller or larger, we cannot determine at this point. Okay, we can guess, but not determine at this point. All right, so this is the end of this video and this end of chapter 10, and I'll see you next time. Bye-bye.